Okay, welcome everyone. I'm Alison from the Southern Cross Postgraduate Association, and today we're here again with Megan Lee to do the final workshop of a 4-part series on statistics and SPSS. And it's been very interesting watching the data develop and evolve and emerge, and I'm sure we'll get a lot more out of it today and see where you're up to, Megan. So people are still coming in. I've posted a few things into the chat box. Just become a member of the SCPA. Be really good. I can see that people have been accessing the last 3 recordings, which is fantastic. You know, there's about maybe 70 views on them actually. So that's good that's helpful, and I'll post the link to the recording out afterwards today. So that'll do from me today. Thank you very much.
Thanks, Alison. Welcome back, everybody, to Advanced Statistics at SPSS. This is the final one of our workshops on statistics and SPSS. What I think is really cool, like Alison said, is that we are watching this data set evolve as we're moving along, and I'm actually doing this live myself. So each week when we're doing the workshops, when problems or issues or data things come up, then I'm building them into the workshops. So it's very, very experiential of what normally happens in when you are analyzing a data set. So some of the questions that came up from last week's multiple regression, we will then do some more post hoc type analyses of what would happen if your data does strange things or things that you don't expect. So as we know, last week, my hypotheses were not met. Part of my hypotheses were not met. So we're going to have a look at today what some of the ways of looking further into why that might be. So I'm a bit excited. Here is my details. If you need me for anything, I'm happy to answer any questions that come up when you're doing your data analysis at any time. I'm also available for tutoring. There is a little fee for that one. If you are interested in following my research after doing the workshops, I have a website, Megan Loving Me Again. It's got all my stuff on it, all my papers, conversation articles I've written, posters I've done for conferences, presentations I've done. All the SCPA workshops are on there, so if you can't find them on YouTube, you'll be able to access them from there. And you can follow me on Twitter, Instagram, and Facebook, same sort of thing. It's mainly talking about my research, lots of stuff in food and mood, and a little bit on student feedback surveys as well. So today we are there was a request last week. Alice, do we email you about tutoring info? Yep, absolutely. Feel free to email me anytime. You can go through the SCPA as well, or just directly to me is easier. Last week we did have a question about, it's all well and good to know how to put your data into SPSS, how to clean it, how to analyze it, how to interpret it, but how do we report our data? So we'll go through the couple of tests that we've done in the previous workshops, and I'll show you exactly how to report in APA 7. The great part about reporting statistics is that there is a system that you follow, so it's almost identical every time you write up a report. So I'll show you the key elements that you need to report and some of the things that I've seen people do in their reporting that's not necessary, and I'll show you how to avoid those kind of issues. Then we're going to move on and we're going to look at logistic regression. Logistic regression basically is exactly what we did last week in our multiple hierarchical regression, but we will dichotomize the dependent variable, which means we'll split it into 2. So last week we used depressive symptoms on a continuous scale between 0 and 60. And today we will take that depression variable and we will categorize it into those who are under the criterion cutoff and those who are above the criterion cutoff for depression, in line with that scale. Then we will move on to ANOVA. which is analysis of variance. We use ANOVAs when we are interested in comparing the averages between groups when we have more than two. So in week 2 of workshops, we did tests. Week 1 or week 2? Might have been week 1. One of them. You go back and watch the recordings, I can't remember. And we looked at comparing the averages of 2 groups, vegans and vegetarians. Today, we will expand that out to our plant-based dietary groups. And we had some questions about, well, what about flexitarians? Are they muddying the diet because they do consume some form of meat? So we'll have a look today. We'll use analysis of variance to see whether or not there is a really big difference between flexitarians and the rest of the plant-based diet groups. Then we're going to have a little introduction to JASP. Now, JASP is another software program like SPSS that's completely freely available on the internet. SPSS is a very expensive program. If you're affiliated with a university, they usually supply it. But once you are out of the university, you no longer have the rights to use SPSS, and it's very, very expensive to use. So JASP is one that we recommend to all of our students at Bond, because it's not a software program on your computer. It's actually an online internet-based software program. It's as good, if not better, than SPSS, and it does some of the trickier analyses like mediation and moderation much easier than SPSS does. So I swap and change between JASP and SPSS. So I'll teach you how to download that to your computer today, and I'll also show you a couple of the things that we've already done, how easy they are to do in JASP. And then we will move on to mediation and moderation. I'm going to do it in JASP because it's so much easier than in SPSS. Do we have any questions today about what we've previously covered before I move on? Feel free to use the chat box. I have it up on one of my screens. Okay, if this is your first time coming to one of the workshops and you have a little bit of SPSS and statistics background, that's completely fine. You'll understand everything that we're going through today. I will go back and discuss some of the things that we did find in the previous weeks. If you find that it's getting really overwhelming, or you aren't quite following what is going on, potentially go back, watch the previous 3 workshops recordings, and then watch this one. Good. Let's go. So APA 7 reporting, way back in week 2, there you go, I answered my own question. We analysed descriptive statistics on our demographics, on all the things that our participants answered in the demographics, including age, gender, type of diet they were on, marital status, education level, age. We took height and weight and we turned it into a measure of body mass index, and then all of our scales. We also looked at a t-test between whether or not there were a difference between our vegan and our vegetarian depressive symptoms. And we found that there wasn't a significant difference between depressive symptoms in vegans and vegetarians. So that overall, the whole population of our data set had similar averages in the depressive symptoms. So we didn't need to move any further with that analysis. If we did our t-test and there was a big difference between vegan and vegetarian depressive symptoms, then we would go and do other analysis to see why that might be the case. But it wasn't, so we would report that at the very beginning of our results section. There is always a paragraph describing our data set. So this is where the descriptive statistics come in, because there are statistics that describe our data set. So here is the table that we would normally provide. Table 1 is always a participant demographic table, and it's got everything in it that we found. So for the categorical data, which is all the very first ones in the table, so diet type, gender, geographical location, marital status, and education level, all our categorical variables, we report N. Does anyone remember what N symbolizes for each category? going back a couple of weeks ago. Number, good, sample size, perfect. So how many participants were in that category, in each category? And what percentage? There's a percentage missing for vegetarians, excellent, Megan. And what percentage that frequency corresponds to? So I think vegetarian was 49%. I don't know why that is missing, but that is okay. The brackets are the percentages and the frequency is the number. Then down here, we've got our continuous variables, age, BMI, dietary quality, depressive symptoms, the DAS, depression, anxiety, and stress scale, social connectedness, and sleep quality. And they all report the means and standard deviations. So outside of the brackets is your mean. So our mean age was 39.6, quite an older set of demographics, to be honest, for nearly 40. Usually lots of psychological research is on younger university age students. So 39 is a very much older demographic than what we're used to, with a standard deviation of 12.7, so around 13-ish. So on average, our data set ranges between kind of 26 and 52. So it's a pretty high age range, which is cool. But when you've got your table, you always put everything in it that you did, your demographics and your scales, all the means and standard deviations of the continuous scales, and then you pick out what's interesting and you report it in text. So I see one of the main problems that I see, or main issues that I see students do, is they'll put their table in and then they'll report everything in the table. And it's like, well, part of APA 7 reporting is not to repeat information. So you just want to pull out what's most interesting, because the reader can go and have a look if they're more interested in other variables. So in this data set, what is interesting? So participant demographic and lifestyle characteristics are reported in table 1. Always introduce your table before it appears. So it will appear underneath this text, and always write, introduce the table in the text. The sample comprised of 164 vegans, 51%, and 155 vegetarians, 49%. That's important because the whole paper is about vegan and vegetarian diet and depressive symptoms. So that's an important factor. Gender split's important. So there were 199 females, so about 62%, 116 males, about 36%, whose mean age was 39.63 with a standard deviation of 12.77. So there are interesting bits. Most participants were from India or Australasia. So we're not going to report all the different geographical locations there. We're just going to say what's most important. And what's most important in this data set is that most of our participants were from India and Australia. Most had a university degree, 83%. That was a really important part of our demographics. That is very high. It's a highly educated data set. So that is hugely important for the reader to know. The mean score for depression was 14.7, which falls below the cutoff of 16 on the CESD-20. So that's really important as well, because that's telling the reader that overall this data set is not experiencing symptoms of depression. So it's quite a healthy data set. Their BMI is quite low, high age, very educated, mostly partnered, so mostly, and from India and Australia. So this is really giving a really good, rich description of what the participants in our survey looked like. So this indicates on average a population sample not experiencing clinically significant symptoms of depression, though they were sub-threshold. So kind of on the threshold of depression, but underneath. So 16 was the, and we'll get into that a little bit more today when we do logistic regression. We split the data set by those who were above and below that criteria. A t-test was performed to explore differences between the vegan and vegetarian groups with all the predictor variables, and no significant group differences were found. So the vegans and vegetarians in our data set seem like they all have similar there was no major differences in any of the variables that we've just described. So they're about the same, which is good because our groups are even. We don't have any wildly older or younger vegans or vegetarians. The vegans aren't much lower in BMI compared to the vegetarians. The depressive symptoms are no different. So that's actually really quite a good thing to describe your data, so that once we move forward and do all of our statistics on the overall population of vegetarians and vegans for life, the reader knows that there was no group differences between the two. Good. Any questions about reporting your demographics? Always your first paragraph in your results, followed by the table. Make sure you always, if you use abbreviations in your table, to put them in a note at the bottom. It does say p-values there. They are not even in there. Okay. So the next part of reporting. In week 3, we analysed relationships using correlations. No, that was week 2 as well. So the second step in doing any form of regression is, or looking at relationships, is to do your correlations. Now, we looked at all of the variables that were significant with depressive symptoms. So CESD20 here, which is the first variable in the column, and then all the other variables in a row. So we can see here each of the variables. So diet quality was significant at the 0.001, social connectedness, sleep quality, the DAS, all the DAS were, but then age, BMI, type of diet, and gender were not significant predictors of depressive symptoms. Marital status, education level, geographical location, and sunlight exposure were. So this is what this correlation matrix is telling us. So when we report our regression, we then, the second paragraph after your demographics is describing what relationships were significant in your data set, and that they will be built into the regression analysis. So again, always introducing your table. Table 2 displays Pearson's correlation for continuous variables and Spearman's correlations for categorical variables. That's why they're down here by themselves, because we didn't do correlations across continuous and categorical, just with the categorical ones are just with the depressive symptoms. So making sure that the reader knows that you did both, so that they're not like, well, why is there categorical variables there when you did Pearson's correlations? So always just describing everything that you did, so that another researcher could come behind you and replicate exactly how you did your analysis. There is a significant negative relationship between depressive symptoms and diet quality. R equals -2.7. Always reporting your statistics to 2 decimal places and your p-values to 3. That's the APA7 rule. Social connectedness, R equals -6.5. Marital status, R equals 0.14. Education level, the R is not there. This is great work, Megan. This is good to know, though, because this came straight out of the paper I'm writing. So I can go back in and fix all the little errors I have made. Geographical location, R equals -0.12. And sunlight exposure, R equals -0.17. There was also a significant positive relationship between depressive symptoms and poorer sleep quality, anxiety, and stress. So it's important to report, when reporting correlations, whether it was significant, what size it was, and whether it was negative or positive. Report the R to 2 decimal places, report the P to 3. And then up in your methods, you would say something along the lines of all significant correlations will be built into a hierarchical regression. Making sure we always introduce our table and then provide the table with the note down the bottom. Any questions about reporting correlations? keeping in mind that if you want to use this as a template for your own research, feel free to paraphrase it out and use that. I tell my students that's the smartest way to do things. Find someone who has reported something and just follow the template of the reporting.
There are a couple of questions there.
Okay, I'll have a look. How did we get R? I noticed the numbers are different in the table. The numbers, so because R is reported to 2 decimal places, the numbers are reduced down. So negative 0.269 becomes negative 0.27. Is anything else different? Social connectedness R equals negative 6.5 because negative 6.647 reduces down to 6.5. Not with a comma in the middle though. Are there any other ones that are different there, Alice? Could you use 95% confidence intervals for correlations, and does it serve a purpose? I've never seen anyone report confidence intervals for this purpose. If your paper was about actual correlations and doesn't move on to regressions, then confidence intervals are a good idea. But at this stage, this step is just to find out what the significant variables are to build into your regression. So the confidence intervals aren't as important. No worry, Alice. Don't worry, I have plenty of mistakes on this board. Education levels R is completely missing. Social connectedness is a comma instead of a dot. But these are all things and why it's so important to work in a research collaboration and everybody goes over your writing. I usually write it up in a flurry, and then people are like, Megan, where's the R for education level? So things like that, it's really, really important to do things with a team because human error is quite large, as we can see here. Any other questions? And we'll move on to how to report the regression. It's looking good. All right. Then we conducted a regression last week. We did hierarchical regression where we built into 3 models. The first model included diet quality by itself. Then we added the demographics, location, marital status, education level. Then we added sunlight exposure, sleep quality, and social connectedness in the final model. Now, when we were looking at the correlations back here, diet quality was significant with depressive symptoms. So as diet quality went up, depression went down. But when we ran our regression, it was still significant by itself. And then it was also still significant when we, it was still significant when we added location, marital status, and education level. So see here, diet quality is still significant, negative 2.82. But then when we add sunlight exposure, sleep quality, and social connectedness, diet quality becomes not significant with depressive symptoms. But also location, marital status, education level, and sunlight exposure all become non-significant when we add sleep quality and social connectedness. So something is going on there with social connection and sleep quality that they are, once we control for them, they cancel out any relationship with diet quality. So that's really interesting for me. It ruins my hypotheses. And it's not something that I've seen happen before in my vegetarian data. So this is really cool and exciting. Just because something's not significant doesn't mean that your data is wrecked. So I know a lot of students get non-significant results and freak out. Their hypotheses are not met. But a non-significant result doesn't mean no result. It means a different result. And you're like, why? Why has diet quality become non-significant when we've added sleep quality and social connectedness? So I'm really interested in that. We're going to look at that today in SPSS and why that has happened. So regression is a little bit more complex when it comes to reporting. Table 3 belongs underneath this paragraph. So that demographics paragraph and descriptive statistics paragraph is first. The correlation matrix paragraph is second, describing which variables were significant to go in the regression. And we've built those into this regression. Then we need to explain a little bit in our regression about how we built the model. So the first paragraph describes how many steps we used, what type of regression, what we were looking to explore. So the association between diet quality and depressive symptoms after controlling for those demographic and lifestyle covariates. Then we describe our steps. So in step one, we put in diet quality, followed by marital status, education level, geographical location in step two, and then sunlight exposure, social connectedness, and sleep quality in step three. The next paragraph is your assumptions testing. But because we went through and did the assumptions testing last week and we found that all of our assumptions were met, then you don't need to do a whole paragraph on assumptions testing. That's another mistake that I see a lot of people do, is they do a whole paragraph saying normality was measured using histograms, box plots, looking at outliers and skew and kurtosis, and there was no problems. Heteroscedasticity, normality, and linearity of the residuals was conducted using the plots, the Z plots of the residuals, and there was no assumptions of the violations. So people do huge big paragraphs when you really need to say all the assumptions of regression were measured and all of them were met. If you do have some violations of your assumptions, that's when you need to build a paragraph. So regression assumptions were tested, all were met except linearity of the residuals, which was seen to be funneled in a scatter plot, something like that. So just reducing those regression assumptions down when you're reporting. Good. Then you move on to what you found. So in table 3, shows the results of the regression. Step 1, diet quality accounted for 5% of the variance in depressive symptoms. So remembering that, we are reporting our adjusted R squared, which is the very, very last column. And it's 5% of the variance in depressive symptoms, which is quite small by itself already. Then you report the F statistic, which is your ANOVA box that we looked at last week. And it is, where is it? 14.46. Can't even find where it is. Oh, because it's not in this table, that's why. Smart. So the F statistics in your ANOVA table that we saw last week, if you want me to show you where that is, we can go back to last week's table and have a look. Degrees of freedom, 1 and 257. The F statistic was 14.46 and the p-value was 0.001. The rest of the data in this table reports the standardized beta, which is as diet quality goes up by 1 standard deviation, depressive symptoms goes down by -0.23 standard deviations. The t-value tells you that that is a significant predictor in the model. And then you've got your R squared, which tells you what the variance is. Now, when reporting regression, we only report the final model that was significant. So in our text, we're telling the reader that when we put diet quality in, it accounted for 5% of the variance and that the ANOVA was significant. In the second step of the model, when we added marital status, education level, and geographical location, a further 5% of the variance. So as you can see here, it's 0.10, which is 10%. And then its ANOVA was significant. And then in the final model, which is model 3, which is here, we added sunlight exposure, social connectedness, and sleep quality, and it accounted for 52% of the variance in depressive symptoms. So if we take that 10% from here minus it from this R squared, which is 0.62, which is 62%, it gives us 52% of the variance. And then we look at the ANOVA box in our data set and find out if it's significant. And then we report those ANOVAs in the text. And then we report the standardized beta, the T for each of the variables, the SR squared, and then the R squared, the adjusted R squared in our table. And then overall, we report that the predictors accounted for 62% of the variance in depressive symptoms. Then we would go on to describe here that once social connectedness and sleep quality were added to the model, that none of the other variables were longer significant. And then we would move on to our post hoc analysis, which is what we'll be doing today. So this is just reporting the main findings of the regression. Your R squared variance and whether or not that was significant with your ANOVA, your standardized betas, your T value, which is what predictors were significant in that final model, and then your R squared of variance. Any questions about regression reporting? And this is just the very simple regression reporting. If we were going to stop here, say everything was significant and we were really happy and we didn't need to do post hoc analyses and look at what wasn't significant, then we would go on to writing a paragraph about the T values. So as diet quality went up by 1, depressive symptoms decreased significantly. As social connectedness went up by 1, depressive symptoms went down by 5.83 standard deviations. And as sleep quality went, well, sleep quality is a reverse one because it's sleep problems, but as sleep problems went up by 1 unit, depressive symptoms went up by 10 standard deviations. That's incredible. Sorry, just realizing what that means. Wow. I'm going to go check out that sleep quality data again, because that is really big. Interesting. Anyway. Okay. So that's where we were up to. Could you explain the 5% and 52% again? Yes, I can. So the first box of our regression from last week is the box of R squared, adjusted R squared, and the R squared change. So between each of the models, model 1, model 2, and model 3, how much our variance changed. So R is like your correlation coefficient. So diet quality and depressive symptoms, that's the relationship between the two. R squared, or adjusted R squared, is how much of depressive symptoms diet quality takes up. So if the variance is 5%, that means 5% of depressive symptoms is accounted for by diet quality, but 95% of depressive symptoms is taken up by something else, other things. Now, when we come down to the final model, which includes diet quality, location, marital status, and education level, we already know from model 2 that all those variables together account for 10% of depressive symptoms, and that 90% of depressive symptoms are accounted by other things. But when we add sunlight, sleep quality, and social connectedness, this R squared jumps up to 62%. So when we remove the 10% that diet quality, location, marital status, and education level takes up, 52% of the variance of depressive symptoms seems to be accounted for by sunlight exposure, social connectedness, and sleep quality. So all that's reported in this final column here. Does that make sense? Yay, okay, perfect. And we're going to have a deep dive into why that has happened. So we're going to go back to our Vegetarian for Life depression data set. I'm just going to see how we're going for time. Good. Very good. Keeping in mind this is live and it's happening as I'm presenting it. So that's why little things are not perfectly polished and interesting and strange things are happening with the data set that probably I wouldn't have reported if I wasn't doing it live. So I think it's actually really cool. So last week, we didn't get to a couple of our research questions. We also wanted to know, does diet quality predict depressive symptoms after controlling for other factors when depression is categorized into those who are experiencing symptoms and those who are not? So we're going to do that today. And we also ask, is there a difference in depressive symptoms between the different plant-based diet groups, not just the vegans and the vegetarians? If we looked at the flexitarians, does their meat consumption influence the data? So we're going to have a look at that now. So to do logistic regression is really simple. If you already have a continuous variable like we do for depression, we can dichotomize it into those who are experiencing depressive symptoms and those who are not. So to do so, I've got to find where SPSS has gone. There it is. To do so, here is our data set. We have our CESD total, which is a continuous score of depressive symptoms ranging between zero. I did not want it to do that. Between 0 and 60, with higher scores indicating greater symptoms of depression and a criterion cutoff of 16. So using that information, we can go to transform. Can everyone see SPSS? Because sometimes it doesn't, or can you still see the PowerPoints?
It looks like SPSS.
Yeah, okay, let's do it. So transform, recode into different variables. Now always do this, because if you rewrite your continuous variable, if you do recode into same variables, you'll lose all of your continuous data from your CESD total. So we don't want to do that. We want to create a completely different variable. Then this little box will pop up. We want to take CESD continuous. We want to change it to CESD cat. I just do cat. And then in the label, we'll call it the CESD categorized by criterion cut off above 16 equals depressive symptoms. And then make sure you click change to change the variable name. Then you go to old and new values. And this box will pop up. And in old and new values, you want to go to range. And you want to go 0 through to 15.99. And you want to give that a value of 1. And then that 1 is going to be not depressive symptoms. And then you want to do a range from 16 through to 60 and give that a value of 2. And that will be your depressive symptoms. Very simple, very easy. Then you continue, press OK. And then at the bottom of your variable list, all the way down here will be your CESD categorical. I always left click on that, drag it up to below the CESD total so they're together, and then just going through and cleaning the variable. So it's got 0 decimal places. We've got our label in there, making sure that our values, value number 1 was no depressive symptoms. Add. Value number 2 was depressive symptoms. Add. Okay. Make sure everything's nice and neat. Now, Does SPSS have the variable correct for the scale of measurement? Is it nominal, scale, or ordinal? Albie thinks it's ordinal because it's in an order. Yeah. I think it's nominal. Why do we think ordinal? Usually ordinal is more than 2 categories, really. I can see your point about why you think it's ordinal, though. I can see your point. I would leave it as nominal. I would use it as nominal. All right. So the next thing that once we've done that, our variables are ready to go. Actually, we should check it because the amount of times I haven't checked my variables and they've been wrong. So let's go CSD categorical here. And we want to order ascending, sort ascending. We've got no depressive symptoms. Right click, sort descending, and we've got depressive symptoms. There's nothing other than a 1 or a 2 in there. Perfect. Okay, so our variable's looking good. Then we can move on doing the logistic regression. So to do the logistic regression is probably easier than doing a hierarchical regression. Now we can build the blocks like we did last week, where we put diet quality into the first block, demographics into the second block, and then the lifestyle covariates into the third block. Completely fine to do a logistic regression. I'm only going to do the diet quality total because the reason I'm not going to run all of them is because the results should be the same. So because it's a regression, a logistic regression and a hierarchical regression should give us the same output. So if we do the blocks again, it will still come out. Diet quality will be significant in the first 2 and then becomes non-significant in the third. So if you do a logistic regression, it comes out different to your hierarchical, then there's something might be a bit wrong. But I'm just showing you this for the sake of showing you how to do a logistic regression. So we won't go through and do all the blocks, we'll just do the first model. So we go analyze, regression. Last time we looked at linear, we want binary logistic. So can anyone tell me why we would choose binary instead of multinomial? Because it's dichotomous, that's right. So we've got depressed and not depressed. There's 2 groups. Good, Zoe, excellent. Multinomial logistic regression is when there's more than 2 groups. So pretty simple. So binary logistic regression, this box pops up. We want to put in our dependent variable, we want to put our categorical CSD total. And in block 1 for our covariates, we'll just pop in the dietary quality. Remembering if you right click on these, you can display the variable names, which is usually easier than the label that you've created them, but you can switch backwards and forwards between that. You can sort them alphabetically or by order in the file. Good. So the next thing that we will look at is if we have any categorical covariates. So if we did put in a block with marital status, geographical location, and education level, we would go in here, click categorical, and we would put those covariates into this box, and we would tell SPSS which category we would use as the reference category. So say marital status, we've got, actually education level might be more intuitive. So education level, we've got like high school, year 10, year 12, we've got bachelor's degree, master's degree, PhD, and TAFE. If we wanted to find out or look at those categorical variables, we would just nominate which one we wanted to measure each of the rest of them to. So I usually put the last category, so the highest category. So I would be using PhD as the reference category to what all the other categories are being compared to. We're not doing that today. So we will just go, you can go to save options in here, and this is where you've got your assumptions of regression. So your standardized residuals, your Cooks, your leverage, and your DF betas if you want. You want to look at predicted probabilities and group membership. Continue. In options, you want classification plots. Cosma, let me show goodness of fit is like R squared in some ways. So you want to look at that. Case-wise listings of residuals. Remember, anything greater than 3 is a cause for concern for multivariate outliers. Correlations, iteration history, and confidence intervals for your exponential B. Now, logistic regression is the same interpretation as multiple hierarchical regression, but there are different words for the analyses of the output. So it can be a little bit more tricky to understand. If you are going to do a logistic regression, I would recommend learning, going and using Andy Field's textbook on IBM statistics and fully reading the regression chapter. And he has steps through multiple simple linear regression to multiple regression to hierarchical regression to logistic regression, and explains how each of the things compare to each other. So it makes it really easy to understand. Okay. So we've only got a very short amount of time today to explain how this all works and all the wonderful world of statistics where different words mean the same thing. So logistic regression is a tiny little bit different to hierarchical regression, where we are comparing the categories of the two, depressed and not depressed. So we are going to look at whether there's kind of a difference between the two people who do and people who do not have depressive symptoms, and whether that predicts diet quality. So the first boxes just tell you how many. We're missing a case. If everyone remembers, we've got 320. So, oh no, I know why. Remember last week where we found, when we were doing our regression assumptions, and we found that participant 175 was malingering and just clicking the same button all the way through, and we decided to remove them. That is why we now have 319, because I removed that person last week. When we are looking at logistic regression, we are comparing a zero block to the final block. Now, zero block is what we would find if we had the perfect model. So if we have here in the classification table in step 0, this is what we're comparing our actual results to. So we have 194 participants who have no depressive symptoms, and we have 125 that do have depressive symptoms, which is interesting because that's a lot more than I was expecting, because our average for depressive symptoms was underneath that criterion cutoff at 14.27, but there was still 125 participants out of the 320 who were experiencing depressive symptoms. Now, what logistic regression does, it states here, if we had the perfect model and we predicted our depressive symptoms and our non-depressive symptoms perfectly, we would get 100% correct, and overall 60.8 of the model. Now, our WOLD value is our statistic for logistic regression. So like our F statistic for regression. and there's our significance. Now, block 1 is the one that we are most interested in, because that is where we entered our diet quality variable. So this is whether we would have a 60.8% percentage correct if we did not include that. Now, in block 1, when we've added diet quality, we have a Nagelkerk square, which is kind of like R squared of 0.129. So that's a lot lower than what the R squared was for the continuous. I think it was 0.26, 0.27. So when we split them by depressive symptoms, our R squared has gone down a little bit. Our Hosmer-Lemichaud test is also significant, so we might have some problems with our assumptions. But what we're really interested in looking at is our classification table. So up here, if we had the perfect model without diet quality and we had about 61% correct, down here, we have 69% correct. So what you want to see in your logistic regression is that once you've added your variable, your percentage correct goes up. So it's gone up by 8%, which means that once we add diet quality to the model, there is a significant change. Then we want to look at our WOLD when we add diet quality. So our standardized beta is negative 0.05. Our WOLD is 28.19. So that's just like our T statistic or our F statistic. Sorry, our F statistic. It's whether or not the model is significant, not the predictor. It's significant. And we're interested in this value here, exponential B. So exponential B is like tells us how much of the variable, what odds we have of our variable being significant. So if you take 1 and minus 0.944, what do we get? One minus 0.944. Is it? 1 minus 0.944. 0.056. So the odds of diet quality and depressive symptoms are quite low, so 0.056. So that is kind of in line with what we saw in our continuous data, right? There was a relationship between dietary quality and depressive symptoms, but the relationship was only very small, about 5%. So again, there's a lot of other data in here that I could explain in a 2-hour workshop. But if you are doing logistic regression, you want a little bit more of an explanation, read that chapter on in field. And I can also send you my lecture that I give my Stats 3 class on logistic regression. I have a question. It's a bit of a throwback, no problems. But in the hierarchical model, if we reverse the order of variables, I assume we would get the same outcome. Why not lead off with what you assume to be your strongest variables? That is a good question, Alison. And we did lead.
It's not from me, actually. It's from Chris. He just accidentally direct messaged me. So that's from Chris.
Okay, no, that's completely fine. That is a really good question. And in fact, I always, when I'm doing regression, I always put my demographics in the first box, my covariates, my lifestyle covariates in the second box, and then I always put my most important predictor last, because then I can see this is what the demographic statistics variance in depression is. this is what happens when we add the lifestyle factors. And this is the unique variance of just my predictor, my diet quality predictor. But when I did this for this data set, so that was the way I did initially, diet quality wasn't significant, which is what we saw. So I switched it around and I did diet quality first, then my demographics, then my covariates to see what happened. And it showed, doing it that reversed order, that diet quality was significant in the first two. And then once we put sleep quality and social connectedness in, it was no longer, significant. So I've done them both those ways, but I would report it the way that we've done it today because it makes more sense to the reader rather than reporting it that there was no diet quality significance at all. So it's much more important, and it's much more information to the reader that diet quality was significant until we added social connection and sleep quality. So I've just reversed that for ease of reporting, basically, because it gives the reader more information. That's a great question. And this is why, like, some of the rules about how you build your models can get thrown out the window, because you're like, oh, why did that happen? Why is diet quality not significant? Let's put diet quality in first and see what happens. Good. So, it's 11:27, so I might just stop, give everyone a 5-minute break, go get a cup of tea, do what you would like, and then we will move into analysis of variance, and then we'll go and answer some of those questions that we have about what's going on with some post hoc analyses and do some splitting the file and mediation.
Okay, see you in 5.
See you then. Okay. So analysis of variance, we were really interested, once we did the t-test and we found out the vegans and vegetarians, there was no difference between the averages of any of our predictors in those two groups back in week 2. Some questions came up about, well, what about the flexitarians? Because they're actually consuming some form of meat, are they not skewing the data? So a really interesting way of doing that and seeing if there was any significant differences in the depressive symptoms between the flexitarians and the other groups is by doing an analysis of variance, so an ANOVA. Now, ANOVAs are really impactful for other reasons as well. You could use them for multiple baseline studies, like pre-post test follow-up. So there's three different groups. And anytime that you have a categorical variable that you would like to measure the averages of. So let's have a look at our analysis of variance for our diet groups, not just vegan and vegetarian, but all of our dietary groups. So we will go analyze. We want to compare means, so we're comparing the averages across groups. Last time we did t-tests. This time we will be looking at a one-way ANOVA. Now, this is our most simple version of an ANOVA. There are very many different ways that you can do it, depending on how your categories are set up. So in our dependent list, we want to put in our depression continuous score. And then in our factor list, we want to put in our plant-based diet preference group, not our vegan and vegetarians, because that would be a t-test. Then we want to look at, just make sure that I get all of the correct boxes. What have we got here? We want to look at our post hoc analyses, and we want to look at our options. Now, as you can tell, I don't do ANOVAs very often because the type of research that I do is very much about relationships and predictions. My friend Victor, he teaches the ANOVA Stats 2 class at Bond, and all of his research is on experimental research. So he is always using ANOVA. So he is the expert on that, not me. We want to run post hoc analyses, which will tell us inside the categories which categories are significant. So inside the analysis, I always run Bonferroni. It's the best one in my opinion. But again, if you read Andy Field's textbook on ANOVAs, he will give you a lot more detail about which ones are used for which types of post hoc analyses. Bonferroni is usually the easiest one. And then in options, we can get some of our descriptive statistics, our fixed and random effects, our assumption of homogeneity of variance, which is the same as homoscedasticity, our Welch's test, Brown and Forsyth, and we can do a means plot. Continue. Okay. Then we wait. Down here, you can see it's running our ANOVA. It's taking its time. Why so slow, SPSS? Here we go. Okay. So the first box tells us some interesting information. So here are our categories that we have done our ANOVA on. Vegans, which include people who don't eat any animal products. Semi-vegans, which include mostly no animal products. Vegetarians who don't eat meat. Semi-vegetarians who mostly don't eat meat. Lacto-vegetarians who avoid meat and eggs but include dairy. Ovo-vegetarians who avoid all meat and dairy but still eat eggs. Lacto-ovo-vegetarians who avoid all meat but include dairy and eggs. Our pescatarians that avoid meat except fish but still eat meat, still eat dairy and eggs. And flexitarians who consume mostly a plant-based diet but occasionally include some meat and animal products. So as you can see, our definitions of vegan and vegetarian are quite flexible. So I don't think that it's possible to do a study on pure vegans and pure vegetarians. We tried doing that recently in a data set of 50,000 Australian women, and we only had 46 pure vegetarians when we analysed their food frequency data. So those who self-reported as vegan and vegetarian, when you looked at the answers on a food frequency questionnaire on meat consumption, they were still consuming small amounts of meat. So yes, it's very interesting when we're writing these papers to make sure we acknowledge that. Yes. So even semi-vegetarian includes mostly no meat. What does that even mean? So they're even in our flexitarians. And this is why we don't do our data on these self-reported categories, because we're just like, okay, we're just going to throw everyone who identifies as kind of vegan into one group and everyone who identifies as vegetarian into the other group. So would every diet option outside literal vegan be put in as non-vegan? It should be, yeah. But we didn't. We put the semi-vegans into the vegan category because they were self-identifying as vegan. But like I said, yeah, how many of these are pure vegan and vegetarians? Not many. Although these ones here, there's 135 pure vegans, which is interesting. Anyway, so it is a good example of things that happen in the real world. Yeah, absolutely. And why we always must be critical when we read any research, because the way that we've identified the vegans and vegetarians and the way that they've identified themselves, is it really purely a vegan or a vegetarian diet? No, it's not. So always being very critical when you read papers about how researchers have identified things. It's massively subjective. All statistical analysis is subjective. It feels like it's not, but it 100% is. Everything is based on how things are categorized, how the researchers have decided the groups will fit together, things like that. So it's very, very interesting. So as you can see here, here's all our averages for depressive symptoms for all of our different diet groups. So we've got 15. So the two vegan groups have an average of about 15. Our vegetarians have an average of depression about 11. Our semi-vegetarians, interestingly, have quite high rates of depressive symptoms. So there's 21, but there's only 8 of those. So that might be skewing that result. Lacto-vegetarians are the lowest. Are lower. The pure vegetarians are the lowest for some reason. Then we've got quite high scores for the ovo-vegetarians. None of this makes sense, right? But the highest is our pescatarians. Our pescatarians have the highest levels of depression. However, what do we not know using these descriptive statistics? What don't we know? So Alice is saying, so the semi and ovo would be considered depressed and the pescatarians clinically above that criterion cutoff. Yeah. N equals 2. For the pescatarians, that's true. That could be influencing it. Very good. What we don't know is looking at these averages, whether or not they're significant. And that's what the ANOVA does. It tells us whether there is a significant relationship or a significant difference between these averages. So these are just telling us what the averages are. So let's go and have a look. Our tests of homogeneity of variance. Do we remember the rule for this? Do we want our assumptions test to be above or below 0.05? Good. So assumptions testing is the opposite to our statistics. We want it to be above 0.05 because we don't want it to be significant, because a significant score on your assumptions means a significant violation of variance. So we don't have that. So that's good. That's really important in ANOVA, because that means that the variances between all these groups is too different and you can't analyze it. So that's good. All of our significant levels are above 0.05. So we can move on to our ANOVA. So the ANOVA box tells us, just like in regression, whether or not our model is significant. So we've got an F statistic of 1.96 and our significant level is 0.051. So what does that mean? This is very interesting in itself. This is a good example to use. Is that greater than or less than 0.05? Just over non-significant. But in statistics, your p-value is either significant or not significant. There is no just significant or just non-significant, which is kind of why p-values are being phased out of statistical analysis and reporting, because the difference between 0.051 and 0.049 is very small, and that criterion cutoff or that dichotomy is a little bit ridiculous. So using confidence intervals, like Albie said earlier, is actually a much greater, gives you much more information than your actual p-value does. Although this is telling us that it's probably not significant, we'll go and have a look. Usually, the rule with ANOVA is if your F statistic is not significant, you stop here and you do not move forward in analyzing the rest of the data. So you do not look at post hoc analysis if your ANOVAs are non-significant. Because there's no point, because the model is not significant itself. Same in regression. If the ANOVA is not significant, you stop. You do not report anything underneath it. So again, our other test of robust equality of means is greater than 0.05. So that's good. Our assumptions are met. Here's our post hoc analysis. We wouldn't report this because our ANOVAs are not significant, but we're going to have a look, especially considering it's on that 0.051 level. Maybe looking at the confidence intervals might help. So what is this telling us? In the model, when we looked at vegans compared to semi-vegans, there is no significant difference. Can anyone see if there's any significant differences between vegans and any of the other plant-based diets? Are there any significant differences there? No, and that aligns with the p-value really of the overall model. Then you can look at the semi-vegans. This is the significance column here. They're all ones. That's interesting. So there's no significant relationship between the semi-vegans and any of the other plant-based diets. There's no significant difference between the vegetarians and the others. So the post hoc basically just tells you if there's any significant differences. I can't see any. So that's giving us a pretty good indication, and also why you wouldn't move forward with doing your analysis if your ANOVA was non-significant, sorry. But it also aligns with what we found when we just split the vegans and the vegetarians in the t-test. There was no significant differences in the averages there either. And then you get a little means plot, which is really fun. I like to report these in my data when I do an ANOVA. It basically tells us here's kind of the means of all the depression, and this is what it looked like. So the vegans look pretty good, goes down, vegetarians are a bit lower, semi-vegetarians a bit higher. As you can see, the highest is our pescatarians for some reason, but our flexitarians, which was kind of the question, right? They seem to be not that much different from the vegans. And our ANOVA also tells us that the flexitarians are probably, this box here, not influencing the data inside the regressions either. What would happen if we took out everyone who actually consumed any form of meat? It would be interesting to find out how many we would have left. Probably not many. Very interesting. Any questions about that before we move on to our post hoc analysis of what's interesting and why, what our new research questions have come up in our analyses? No, everyone's still with me. That's good. So now that we've done our initial analyses to answer the research questions that we had, that we were hypothesizing before we did our analysis, and it's very, very important to have your research questions written down before you do your analysis, so you don't go off and start hypothesizing after the fact, after the analysis, because that's very, very bad. Lots of people will not hypothesize about their research question and just run correlations and be like, these are all the significant ones, we'll put them into the regression model, and then whatever comes out in the regression model, then we'll turn them into our research questions. That is not good. That is a very, very bad practice. Please don't do that at all. Please don't do that. But what we're doing now is not hypothesizing after the fact, and it's not creating new research questions from our analysis. It's post hoc analyses of answering why certain things happened in our data set. So we've got two new research questions. Does diet quality predict depressive symptoms between those who are above and below that criterion cutoff? Now, the logistic regression didn't tell us that. It just basically told us if there was a difference in the predictions between the categories. So to do this, we need to split our data set into two, those who are depressed and those who are not depressed, basically. And then our second question that's come out of this is, does social connectedness mediate the relationship between diet quality and depressive symptoms? Now, why we've developed these two new research questions, the first one about clinical and non-clinical participants is because diet quality has become non-significant. But the question that I have is that because, and what I found in all my other research in my PhD was that depressive symptoms, diet quality is usually influential in depressive symptoms in those who don't have clinical symptoms. So it's a preventative rather than a treatment. So it's for people who are kind of sub-threshold, who are not experiencing clinical symptoms of depression, who would like to use healthy dietary patterns to prevent them from getting those clinical symptoms. But once people tip over into clinical depression, diet quality no longer really works. And we found this in our other research. It's across all of the data. So depressive symptoms, and why we use depressive symptoms in our research, is because it's not for major depressive disorder. It's for those people who may be experiencing subsyndromal depressive symptoms. So what I want to do is I want to split the data by those who are and those who are not clinically in the cutoff, and see whether or not there's a difference in the regression. And then the second one, because when we put social connectedness and sleep quality into the regression and diet quality became not significant anymore, I think that maybe the way that we eat socially may be mediating the relationship between diet quality and depressive symptoms, which means that if we eat by ourselves at our desk, eating a salad, we're not going to get as good an impact on our mood as if we went down to the cafe with our workmates and ate a burger. That's my other hypothesis. So we're going to try and see if that's correct. Any questions about our new research questions and why they have been developed this way from the data that we have run last week? Okay, let's move on then. I'm going to teach you how to split the file. Now, one thing that you need to make sure is when you split any files in SPSS, it stays split even after you exit out of SPSS. So next time you come back into SPSS, your data will still be split by these categories that we're about to split by. And that can be very confusing if you go to do a new analysis and you're like, what is happening? Everything is still running. Yeah, it's very confusing. So one of the things is to make sure you don't forget to unsplit the file before you conduct future analyses. But let's go in and have a look how to split the file. So we go to data, split file, little box will pop up. We want to compare groups, and we want to compare groups on the categorized CESD. So this is where we use the categorized one. So it's going to split the file by depressed and not depressed. Okay. Now you can see down the bottom here that the output is still the same. Nothing has changed in the output box. You can see down the bottom here, it says split by CESD categorical. It's very small and hidden away in the corner. Don't forget to unsplit. All right, now we're just going to do the exact regression model that we did last time. So we're going to go regression. We're not doing the logistic regression. We're doing the regression on the continuous data. So this is where it can be a little bit tricky because we've just split the file by the categorical depressive symptoms, but now we are going to run the continuous CESD, or the continuous variable on depressive symptoms across the two. So that can be a little bit tricky. So regression, linear, exactly the same options as last week. So we put the continuous variable for the CESD. We will change the variable names around so it's easy into that box. Start with diet quality. Block 2, we did marital status, education level, and geographical location. And then in the final block, we put social connectedness, sleep quality, and sunlight exposure. Then in statistics, a little pop-up box will come up. We want to ask where change between our variables. We want part and partial correlations, our collinearity diagnostics. our Durbin-Watson, which is our assumptions. Case-wise diagnostics will tell us our outliers. We can get a covariance matrix, confidence intervals, and our descriptive. So pretty much everything in that box. Then we can build our residual plots just to see if there's any multivariate outliers. So the Z residuals with the predicted variables of Z, we can get histograms, normality plots, produce all partial plots. Then in SAVE, we can get our standardized residuals, ANOVA. This will also tell us about outliers affecting our data. Cooks. Continue. Okay. And then the bootstrap button is only if your assumptions are not met. Then you would use bootstrap. Okay, let's go see what our data tells us and whether it's different from what we found last week. Keeping in mind, these regressions are split by vegan and vegetarian now. No, by not by vegan and vegetarian, by depressive symptoms and no depressive symptoms. But if our t-test way back when in week 2 told us that there was a difference between vegan and vegetarians, we could also do this for the 2 diet groups. So for those who experienced no depressive symptoms, their average depressive symptoms were 7.6. How does that differ to the average across the entire population that we found? Do you remember what the average was? It's half. Good. Yeah, so it was 14.27 or something like that. So those who don't experience depressive symptoms, those who are under the criterion cutoff, their average depressive scores were 7.6. Their dietary quality was 67, so that was between 0 and 105. I don't remember. I think that's about the same. Social connection, look at that, 89. Good. Sleep quality, that should be low because remember higher scores mean more sleep problems, so that's quite good. Those who had depressive symptoms, let's have a look. Their average CESD score was 25.04. How does that compare to the overall population? It's over double. No, it was 14.27, so it's just under doubled. So those, and this makes intuitive sense because those who are above the criterion cutoff would be more than those who weren't. So we've got kind of a bit of a double mean really in the data set, which is being skewed by and looking like a normal distribution. Those with depressive symptoms, though, have dietary screening tool is 60 compared to those who don't have at 67. So the diet quality of those without depressive symptoms seems to be higher than those who do. Social connection is lower as well. So 89 for those without and 71 for those with. Sleep quality, there you go. Sleep problems are higher in those who are experiencing depressive symptoms compared to those who aren't. The sunlight exposure is about the same. So again, these are our descriptive statistics. What are they not telling us? If the results are significant, good. So it's just giving us kind of a description of what we are finding, but it hasn't told us if they're significant. So then again, we have correlations, but these correlations or the relationships are now split by not depressed and depressed. So we just want to look at this first column, which is the center for the depression scale. Interesting. One sec. Where are the significance levels? There they are. Okay. So split in a weird way. So we've got the actual relationship here, negative 0.129 for those not experiencing depressive symptoms, which was the same as when we did the logistic regression, and it should be because it's the same correlation, and it's just significant at 0.048. So that's for our not depressed. We've got R squared, negative 0.129, and just significant. But for our depressed category, dietary screening tool is 0.09. Weird, it's not even negative. Ooh. And our significance level is 0.183, so it's no longer significant. So what we're seeing here in just the correlations is that those who are not experiencing depressive symptoms have a significant negative relationship with diet quality. As diet quality goes up, depressive symptoms go down by 0.1. Well, the relationship there's about, got to work that out. 0.129. I've got to square that. Can't square 0.129 in my own head. That'll tell you the variance, not much. But those who have depressive symptoms, the relationship is 0.09. It's a non-significant, but it's positive. So as diet quality goes up, depressive symptoms go up. And that doesn't make sense, right? But it is non-significant, so you wouldn't interpret it that way. So this is just telling us what the relationships look like. We can then move on to our regression. So this box just tells us what variables are in each model. You check that to make sure that you haven't made a mistake. Diet quality, demographics, and in the final model, everything all in together. Here is our model summary. So this tells us our R squared, the variance. So I don't have to work it out by calculating it in my own head. So for those people who have no depressive symptoms, diet quality takes up about 0.01, so 1% of depressive symptoms. So 99% of their variance is with something else. Once we put everything into the model for those who don't have depressive symptoms, it's 0.27, so about 28% of the variance. So that's very different to our hierarchical regression when we put everybody together. For those with depressive symptoms, again, diet quality is doing weird things in that first model, although it's not significant. Oh, nothing is significant except for the third model in no depressive symptoms. So there's some really interesting things going on. Let's go and have a look at the ANOVA. So the ANOVA box tells us whether the model is significant. So with those who have no depressive symptoms, is model 1 significant with dietary screening with the diet quality? Over here. Nope. What about when we add the lifestyle characteristics? I mean the demographic characteristics. In model 2, is the ANOVA? Nope. What about in model 3 when we include social connectedness, sleep quality? Yes. So in people who don't have depressive symptoms, diet quality by itself is not significant. Demographics by themselves are not significant. But when we add sleep quality and social connectedness, everything is becoming significant. And the same thing in depressive symptoms. So that's when you would go down to your coefficients and read the third box. And again, when we looked at no depressive symptoms and we look at the T values and the significance of what in that third model is significant, what do we find? Diet quality, not significant. Marital status, not significant. Education level has become significant in those who don't have depressive symptoms. Geographical location, not significant. Social connectedness is. Sleep quality is. Sunlight exposure is. In those with depressive symptoms, in that final model, diet quality, not significant. Marital status, not significant. Education level is. That's interesting because it's not in the overall. Geographical location is not, social connectedness is, sleep quality is, sunlight exposure is. So the same sort of pattern. So even splitting it by depressive symptoms, we're seeing the same thing. Very, very interesting indeed. which is interesting because last time we did this, on a vegan and vegetarian dietary group, when we did the split between the clinical and the non-clinical, we found significant results for the not depressed and non-significant results for the depressed groups, but it's different this time. Very, very interesting. Any questions about interpreting that split regression? Again, we've gone through all these assumptions testing. Any questions? Cool. Very, very interesting and insightful results. Now we want to go back to data, split file, analyze all cases, do not create groups, and click OK. And then down here, it does not say split by CSD categorical anymore. All right, the final analyses. We've got 23 minutes, and I'm going to teach you how to use JASP, which can be a really good alternative if you don't have SPSS or you get kicked off SPSS. It does all the things that I've shown you in SPSS. The only drawback of JASP is that you can't manually put your data in and you can't manually change the data once it's in. You have to bring it in from Excel or SPSS. So you can't type in like you can in SPSS. You can't change variables, stuff like that. So this is where you go to download JASP. You can do this now or you can do this later. These slides or on, you can watch the recording, stop the recording at this slide and follow the instructions. It's really simple and really easy. When you get into JASP, just make sure, because it looks like this and you feel like what's going on, don't ever click this because that's what it feels intuitively like you should do next. Don't do it. Just click this little box here up the top. The 3 lines at the top, don't click this, click this. And then you bring your data in from anywhere you like. So you can bring it in from the computer, you can bring it in from a data library. JASP has stuff in there. You can bring it in from Open Sciences framework. It's actually very cool. And you can bring data in any shape or form. So from any other software program. So I'm going to go and find this data set. There it is. And open it in JASP. And it looks very similar to SPSS. So you've got each row is a participant and their answers on all the variables. Each column is your variable, but there is no data view and variable view to switch backwards and forwards between. So it can get a little bit more confusing when you're trying to play with your data, but you want to clean it when it's in Excel before you put it into JASP, because you can't really do too much data cleaning in here. But I'll give you a little bit of a spin. So descriptive statistics, what do we look at? Let's look at our CSD total. So as you click your variables, the analysis pops up on the right-hand side immediately. So you can see here we've got 319 participants, 0 missing. Our average CSD is 14.27, which is what we found. Our standard deviation of 9.95. Our minimum CSD score was 0, maximum was 43. You can split the data here if we wanted to by categorical. So immediately that split that data by depressive and no depressive symptoms. So in saying that SPSS is easy to use, this is also much faster and funner. You don't have to be clicking through things. You can look at things, you can take them away. So we can get rid of that immediately and then just go back to our original one. So it's a lot less work. We could split depression by our vegan and vegetarian group as well. And we can bring it back if we're not interested in looking at that. We can do some frequency tables. That's probably not the best thing to do on a continuous data set though. You want to do that on your categorical variables. Remember the descriptives that we looked at with the N and the %, that's your frequency tables. So maybe we'll do that. Put CSD back, have a look at the vegan and vegetarian groups. There you go. So at the top, it gives you your mean, which doesn't really make sense for your vegan and vegetarian groups and your minimum and maximum because they're categorical. But then down here, it'll give you how many are in each group, what % that is. And then you can bring that back in. So you can do your descriptive statistics really quickly and fun. So let's have a look at some of the plots we can do. So we can do box plots of our demographics and see this little dot there. That is our outlier. So number 220 that we didn't get rid of. The bar in the middle is your median, your interquartile range here, and then your whiskers are your most extreme scores. We can also do, see, and things are called different things. So our histograms are actually called a distribution plot. So remember our histograms are skewed in SPSS, same sort of thing here. We can look at correlation plots. I believe that's our scatter plot. Is it going to come up? Oh, because scatter plots need 2 variables, that's why it's not working. QQ plots will give us the skew around, so that's how one of our assumptions tests. We need 2 variables to do a scatter plot, so let's put diet quality in. And then it'll just produce all of our descriptive statistics for diet quality. It'll do our diet quality histogram and box plot. It will do our QQ plot, and then we can do a scatter plot of diet quality and depressive symptoms. Will it allow me to? Box plots, there it is. So, oh, look at that. That's interesting. It looks curvilinear, doesn't it? It doesn't look like it's a straight line. Anyway. And then you can click on statistics and you can look at, and it'll come up in this box up here. You can look at your median and it'll just be immediately added to the mode. You can look at your interquartile range, your Shapiro-Wilks test. So that's your normality test can be put in there. So you've got all these options that you can do inside of JASP. It's really, really handy and fast. So much quicker than SPSS. All right. So that's your descriptive statistics. You can do your t-tests. You can do regression. We are going to do a mediation. Does JASP export in APA7 format? No, it doesn't. I don't think. No, it doesn't. But you can copy and paste directly from JASP into Word. I think we'll have a look in a second. Now, for mediation analysis, it's really complicated in SPSS. You have to like download another software link in SPSS called Process, and it's a very complex thing to do. But in JASP, you just go to structural equation modeling. I don't know why it's in there because I don't consider mediation to be. We've got to get rid of the descriptive statistics first. There we go. And we want to do mediation. Right, cool. Now, our predictor, I've got 2 of them there. I have to make sure I get these in the right order. Okay, so you can tell me, what's our predictor? What have we been looking at? What is our variable that is our predictor or our IV? Good. Diet quality, and it goes. What's our Depression. Put that in to outcome. Which one is it working on? And then what were the mediators that we were trying to look at? So when we did the hierarchical regression, what cancelled out diet quality? Sleep quality and no, some didn't end up being significant in the final model, which is interesting. It was sleep quality and social connection. Social connection is a very interesting one. It always comes up as like the highest predictor usually. So let's do sleep quality next. We'll do social connection first. Options, we can look at our squared. We've got our confidence intervals at 95%. We want a standard method, but if our mediation assumptions were not met, which are the same as the regression assumptions, we would bootstrap. We're looking at total indirect effects and residual covariances. Do we want a model plot? Yes, we do. We want a model plot on our parameter estimates, and it will give you the figure that you put into your report. And this is why I love this so much. Come on, please do it. Yay. So doing this figure in SPSS is impossible, but it just does it for you like straight away in JASP. And this is one of the things I love. Alice has a question. I found this particular book extremely helpful with SPSS stats, step by step. A practical guide by Allen and Bennett. Yes, that's really good. Allen and Bennett is another textbook that I recommend. It's a very step-by-step how to do the statistics. It doesn't really give you the theoretical background behind why what happens in each analysis like Field does, but it's really, really good complementary to that because it's very simple. Is there one on it like it for JASP? We'll have to have a look. All right, good question, Alice. I'm going to remind me to answer that and we'll have a look. Okay, so this is our mediation analysis of social connectedness with diet quality and depressive symptoms. Basically, what it's telling us is that there is, so the direct effect of diet quality on depressive symptoms in the model. So the direct effects is just the predictor and the outcome. It's significant, which is what the regression told us. But when we add social connectedness here in the model, social connectedness fully mediates the relationship between diet quality and depression symptoms. So that is telling us a lot of information. So you would report kind of the same way as the regression, and you would put this figure at the bottom. And this figure actually has all the information on it that says, yes, there's a significant relationship here. But once we add this, social connection fully mediates this relationship. So what that means is that if you're eating in a social way, then it's the act of eating socially that is influencing the depressive symptoms and not the quality of the diet. So the overall key takeaway is if you eat a salad by yourself, you won't feel as good as if you go and eat burgers down at the cafe with your friends, basically. You have to make sure your burger's plant-based though for it to work because it's in vegan and vegetarians. But yeah, very, very simple to do in JASP. Now, I want to go back to Albie's question about whether or not this, it looks like it's in APA 7 to me. Let's go see. So how do we get this to, copy. I'm going to open up a Word document and see what happens when we paste it. Ooh, that's actually quite good. So the answer to that is yes. It's in APA 7. That looks pretty good to me. You would just remove these types of things. Yeah. Make some spaces. Yeah, so it's completely, yeah, that looks better. Looks like it's in APA to me. What about the figure? Let's do it. Copy. Oh, you can save it as an image too. Perfect. Yep. Just remove the bits that aren't. It is a picture though, so you can't edit it by the looks of things. Oh, what have we got in the chat box? Alice found. Let's have a look. Oh, I don't know. We're just waiting for that to open. So in the chat box, Alice has very kindly, thank you. Statistical Analysis in JASP, a guide for students by Mark Sampson. Oh my gosh, look at that. Thank you, Alice. That's perfect. Oh, and it starts from the beginning, like downloading it, how to get it into your computer, bringing in a data set. Oh, great find. Good job. That's it from me. 7 minutes to go to answer any questions that you may have. I have really enjoyed this one. Are you able to explain why it is mediation and not moderation and give a moderation example? Oh, that's a good question. My Stats 3 class. This is one of actually the questions that I put on the Stats 3 exam, because the difference between mediation and moderation is tricky to explain. So wait 1 minute. The best explanation I ever found for mediation and moderation in a very simple and easy to understand way without it getting too complex was on ChatGPT. So I'm going to use that and show you at the same time how to effectively use ChatGPT to answer your questions. It's actually really, really helpful for things. I use it all the time now. We were scared of it when it first came about because we thought students would be using it to write their assessments, which they probably will. But it's actually very, very good for statistics. You can put a data set into ChatGPT and it can analyze it for you, which is pretty exciting. Okay. Obviously, I can't ask this question on exams anymore unless it's invigilated. Then we can also ask, will it be smart enough to answer that question? There you go. That was a good question, Elizabeth, because social connectedness can be a mediator and a moderator. That's pretty cool, hey?
Very good.
So if you are doing mediation or moderation and you don't know how to interpret what has happened, pop it into ChatGPT and it will help you. Don't copy and paste ChatGPT into your paper though. Paraphrase out the interpretation, but it's really handy in helping you understand what's happening in your analyses. I realized I didn't do sleep quality, so I will really quickly put in sleep quality. We can put them together, which is really cool. And then the mediation will look like this. So this is with sleep quality. What's happening here? Same thing. Sleep quality fully mediates the relationship between diet quality and depressive symptoms. And that will change our interpretation of our paper. And I think that's a good thing, because even though my hypothesis wasn't achieved, another one of my really interesting hypotheses was, so I really believe that social connection, and in my PhD, this came up even in the general population, especially in focus groups when I talked to people, they always talked about the social aspect of food and how that increased their mental health. Culture, cooking together, having a wine and music on in the background, eating together mindfully, not eating in front of the television by yourself. All these things were coming up, and it time and time again comes up in my research. So I find it really awesome that although my diet quality hypothesis was not supported, what I believe about social connection is every time. When do you use mediation in your analysis? So mediation is commonly used in analysis in this particular situation where you know, or your regression has shown that something is impacting the relationship on another thing that was significant, but when you add it, it is not. But you can also do mediation analysis. Mediation can actually be a research question. So if there's lots of papers out there about diet quality and depressive symptoms, and like me, you wonder whether or not social connection mediates that relationship, then you can just write a whole paper on, well, I hypothesize that social connection mediates that relationship, and you can just do a mediation analysis. Yeah. We did a paper on I think it was moderation between body image and intuitive eating in postpartum mums. No problem.
Very good. Thank you so much.
No problem.
So you're writing up now, Megan?
Yeah, we're writing up now. What I'm actually thinking is next year, if you want me back to do these again, I might use this same data set,
yeah,
but give everyone the data set. I couldn't do that this time because the data set's live and
yes,
yeah, you can't.
That sounds great.
Do that. But next year, once it's all written up and it's published,
yeah,
I'll give everybody the data set and then they can play along with me as we go.
That's a great idea.
Yeah.
Yeah, I suspect we will be offering again next year for sure.
Yeah, cool.
Okay. I liked your comment earlier. It's better to go and have a burger with friends than to, what did you say? A plant-based burger, that is. Than to have a bad night's sleep or eat alone.
And it's interesting when you look at the demographics for this paper by themselves as well, that the vegetarians and vegans have really good like markers of health, like their BMI is really low, they're highly educated, their depressive symptoms are quite low compared to what we normally see. Yes. All those types of things, that it's very interesting because they get kind of slammed for nutrient deficiencies in their diet, things like that, when really the analysis that we can see here, they've got actually really good health and diet quality.
Right. That's right. They get a bit of bad press, huh?
They do, the whole thing. And for anyone who's wondering, I actually am not vegan or vegetarian.
Aren't you?
No. I eat more plants. But I
Yeah,
still eat meat. So
yeah. Cool. That was very good. There's some very good feedback there in the chat box. Excellent. Thank you. Did you want to ask something, Zoe?
No, just I will be in touch. Because I did contact Alison late last year to say that stats was really my weakness, and so they were going to put me in touch with you. So I thought I'll do this, work up my project proposal, and I'll be in touch at the design phase. Yeah.
Hey, sounds good.
perfect. Sounds great.
Excellent. Okay, we'll finish up there. I'll just stop recording.